Okay, so here now it's time to look at the last sort of class of molecules that we're trying to make is the nucleotides. Okay, and we're going to bite the bullet and we're going to start with the hardest one here, purine biosynthesis. It's not really the hardest, actually. People are remarkably good at this, and it may be the most complicated. Okay, but for some reason it's not that hard to master, and we're going to start with something. I'm going to start with this thing way up here. There we go. I'm just going to draw it like this. There we go. So what have I drawn there? This thing is, of course, ribose 5-phosphate, otherwise known as 5K1-omega, which we can get from the pentose phosphate pathway. We can get from the Calvin cycle. Okay, so we take this thing, and this is going to be a very expensive process. You know, DNA is a very important thing in the body, but it's also very expensive to make. And we can start to see this expense. We're going to see so many ATP used in almost every step, and when we're not using ATP, we're going to be using other energetic molecules. So here, we're going to add ATP. In fact, we're going to add 2 ATP, which of course by now we know 2 ATP equals ATP going to AMP, and then we're going to rephosphorylate it. Okay, there we go. That means we're transferring both phosphates, ATP to AMP, and what we're going to get is we're going to get this molecule. Now I'm going to draw it a little cartoonish here, and I'm going to allow you to do this here because the biosynthesis of the nucleotides is really the biosynthesis of the base, not the biosynthesis of ribose, which we know how to get ribose from glucose, Calvin cycle, or pentose phosphate cycle. Okay, so I'm just going to draw this PRPE. Okay, there. One time I'm letting you draw some cartoons here. And just like now what we're going to do is we're going to transfer our nitrogen. We're going to start building it on the nitrogen. Okay, and the nitrogen donor we're going to pick is the highest energy nitrogen donor, Q. And when Q donates its nitrogen, remember it took Q, E plus ammonia plus ATP. So this is equivalent to an ammonia and an ATP. So it's really equivalent to another ATP here. And when Q donates, goes to E. And now we're going to get something here. It's just going to, last time I'm going to draw this PRN. Okay, that's going to be the first nitrogen of our base. Okay. Remember when we learned the bases? We learned purines. I'll put up here purines. We learned this thing. How do we know what the bases are? I had this pattern of NC, NC, right? N, C, N, C. N, C, N, C, N, C, right? And if you put this all together, this is how you can learn the nitrogen substituent. And some of you who didn't know that, and you got to review that and go back and learn all your nucleotides. This is adenine, like this, right? So it's kind of like that in the biosynthesis. We think, primordially, we think this was made by a polymerization of a whole bunch of cyanides ions, okay? Various things like that. Okay, so the biosynthesis, other way around there. So this one's kind of a funny one here. Okay, so the biosynthesis of this, and see, the biosynthesis of this thing is going to kind of recapitulate that, not with cyanide because that's a deadly poison, but we're going to add atoms one at a time, almost all the time. As a matter of fact, except in one step where we're going to add 2 N's and a C. So we've added an N here. The next thing here, we're going to have to add the C, and the next step is where we're going to add this. Instead of just a C, we're going to add a CNC, and in fact, we're going to add this thing, glycine. Okay, and we're going to add glycine to this thing, and we're going to have to form a peptide bond. So now, this is what I'm saying about not drawing the rest of it here. I'm just going to draw this. We're forming a peptide bond with glycine, and of course, this requires energy to form that bond. And that means we're going to use another ATP right here. Okay. Now we've seen this, that yeah, that's fine. Yeah, this other glycine here. Now we have to add, so this is N, CNC. So now we should be up to adding another C, right? So what we're going to do here is we're going to take this thing. We know that glycine can also decompose. This reaction can compose into this thing called methylene THF. So we're going to take a little detour into THF a little bit to understand this. Okay? the THF, we know that we have this thing, methylene's a 1. So this thing here is really, and I'll put this thing in the middle in blue. It shows up a little better than green. Okay? And this thing we think is functionally equivalent to, what's the oxidation thing? This is equivalent to what? Equivalent to a Schiff base, right? And this thing, so this thing, and it's also, which would be equivalent to formaldehyde. Right? This is a caged formaldehyde. Okay? Instead of forming a Schiff base with just one nitrogen, we're forming basically kind of a split Schiff base with 2 nitrogens. That's the way we kind of understood this. I can take formaldehyde and I can oxidize it, or I can reduce it. Okay? So if I were to oxidize it, I would take my blue pen here. I would take electrons out, or I could put electrons in. And if I reduce formaldehyde, I would get, okay, if I reduce it, I'm going to get methanol. And if I oxidize it, I'm going to get formic acid, right? So in reality, all these things are toxic. Formaldehyde's toxic, methanol's toxic, formic acid is toxic to you, okay, in varying degrees. Formaldehyde is probably the most toxic. Methanol's fairly toxic. Don't drink like moonshine, right? This illegal whiskey has too much methanol in it compared to ethanol, which is relatively harmless. So we can do the same thing inside THF. So this is one, so this is called N5, N10, methylene, THF. If we reduce it, we can get something like this. We can get methyl THF. Okay. And this is equivalent, check the oxidation state. This is just really CH3. This is equivalent to methanol, right? And so this would be called, N5, or we can have N10 methyl THF. Okay, methyl, methylene. Okay, and what we can do, so this is a process, we take it here, and it's the same thing, equivalent. We're going to put electrons in to do that. And we could take it, and we can also oxidize this thing, and we would get this thing. I should draw this in this green color, blue color, I should say. There we go. This thing, or we can also get this thing, and these things can then hydrolyze to, of course, this is in fact kind of a Schiff base here, and so we would get formal or formal. All right, so I get N5 or N10 formal. Okay, so these are all the different states of one carbon metabolism. The entry point is always, what's our entry point to produce these compounds? We always come in right here to this thing. This is the central one. This thing equals 1. Okay, and we can make this from glycine. We can also make this, and when we make this from glycine, we spit out ammonia and CO2, and it's a reducing thing, or I can make this from serine, right? And in the process, we go down here. Serine is going to split this off into that compound, and we can make serine, effectively, all the way, if you run the photorespiration recovery pathway backwards, PRR, we can go all the way down from glucose, and we can actually get serine, and then we can get glycine, and we can get 1 all the way backwards. And you know this pathway. This is photorespiration recovery pathway, okay? We can go like this. There we go. Okay, into this central one, and then we can oxidize or reduce this 1 carbon thing, this formaldehyde, this caged formaldehyde, up to methanol or down to formic acid. And formic acid is important, like for instance N-formal methionine from your cell biology, right? Translation always starts not with methionine but N-formal methionine. Okay, so here we see this now that was our little detour. We can get formal THF, by, right here, taking this, and what we're going to do is we're going to oxidize it. Yeah, let me show all these things in here. Glycine. I guess I should show CO2 and or NH3. There we go. Okay. So I can take this formol now, and I can add it right here. Okay. So I'm adding a formate. And now this is stored up on THF, so it is kind of a high energy compound again. And I don't need to use any ATP in this one step because it's already on something, and I'm just transferring it from one thing to another. Okay. All right. Now what we're going to do is we're going to take now. So this time we added a C. So I'm thinking, okay, let's just go through what we've done. We added an N right here, and then we added a C and CC, a CCN. Now we've added a C. Now we have to add an N here, right? N, CCN, C. Now we have to add an N. So let's do our thing here. Let's add Q to E. And in this case, this was already highly activated up here, pyrophosphate. Essentially, these two ATPs have activated this and put in that energy, so I can transfer it easily, even though this is an N. Here we have to add another ATP. And this becomes the beginning of the first of 4 steps in a row. We're going to add ATP. It's going to be really kind of cool. And you can remember that. 4 in a row. ATP, ATP. Now here. A. Okay? So what we're doing is we're going to transfer it down to this position here, and we're going to get this kind of compound. Okay? The thing is, we're sort of forming this Schiff base, but this is going to be delocalized into this peptide bond, and this is why it requires energy. This kind of resonates, right? We know the peptide bond has this resonance structure like this, okay? And so we can't form this Schiff base very readily, right? And that's why we need this energy in here, right? We have this resonance thing. About 50% resonated, it's sp2, and so we can't form this Schiff base without any extra energy, so we have to add extra ATP to do this. Actually, it kind of phosphorylates this thing, and then we can have a leaving group. Same thing down here. We're going to actually, in the next step, we're going to form the ring, and it's going to require ATP. Remember I said 4 steps in a row, so here's another ATP requiring step. Okay, and we're going to form the ring. Now, the way this works, you don't have to, this is the intermediate, you don't really have to know this, but to think about what are we trying to do? We're trying to form that first ring of purines, that 5-membered ring, and we're trying to form this thing. Okay. And if I do the rest of it, that's the beginnings of ATP here, right? Or of a purine. Okay. Well, what's happened here, how do we do this? These things, I have to form this double bond and this double bond. These things both resonate, right? So I can show these different resonance structures of this. I can say this thing is going to resonate. Okay. In reality, it exists about 40% this way. And this thing exists maybe about 30%, a little less for the nitrogen. Okay. This is a valid resonance structure of this. Now, in order for this to happen, what we do is we take the ATP, and the ATP phosphorylates this site, so we have this thing. And you don't need to show any of this, but this can help you to understand what happens here, right? And now this thing can attack and displace that phosphate and come up into there. Hey, how good? It's like one of those mini mechanisms. I could make another mechanism for you to learn, but we learn a bunch of mechanisms. We have enough mechanisms. Okay, so what have we done here? So this is not, we haven't added an atom, we're just closing it up, so we're due to do a C now, right? Where's my pencil? C. Okay, N, C, C, N, C, N, C, and then the next step must be an N. Okay, just to look ahead. So here we're going to add a method we know many times. We're going to add CO2, biotin dependent. And of course, when we do the biotin dependent, we need ATP to get it onto biotin first. So it's an energy requiring step. And we're going to add it up in this position up here. There. Now, another energy requiring step. We're going to come up here. And we must be adding N. We're going to add a different nitrogen donor this time. This time we're going to add D as a nitrogen donor. Okay? D is a nitrogen donor, and it's going to add an N. And we're going to go through an intermediate, because when D acts as a nitrogen donor, it always binds to something, and then it's released as fumarate. right? Just like in the urea cycle. We're going to see this in one more spot. Isn't that really cool? And we're going to get it. And I'm not going to draw this initial structure first. I'm going to draw the second structure. Okay, adds it into this next position. Okay, so this intermediate, now you have to show the intermediate, but you can tell what it must have been now a lot easier. Sometimes if you think what's happening, this is a nitrogen we're adding, so it must have been this thing. And we're adding D, so there you go. And all these compounds have, you can look them up in the textbook, they have big, long, ridiculous names. You know why we would name them. Okay, so we add D and we release fumarate to leave its nitrogen behind, and this, of course, requires ATP. So as I said, 1, 2, 3, 4 steps in a row requires ATP. Now I've arranged this in this U because it's kind of cool. What happens is we're going to add, right here, we're going to add another one of these things. We're going to formulate one more time. Sort of at the same spot in the U. If you come down and go up again, it sort of forms naturally, because now we're due to add a C. Right? Here, this is sort of 2 steps to add this N. Now we're C, N, C, C, N, C, N, C, N, C. Another formal. Onto there. Okay. Now we have ring closure. We can kind of form a shift base here. Now this is like an intermediate. Okay, I could say, well, I could form this thing. A kind of crazy looking shift base conjugated into here. Okay. Now, this is not really the proper way to draw the Kekuli structure, so this is going to resonate up into here, right, to form a proper benzenes type structure, right? And what we're going to get is we're going to get this base that you had to learn a long time ago. In addition to ACGT, what other base did you have to learn? And you need to learn one more base, and it's called I. There you go. And I can now I'll put the rest of the structure that we haven't been showing all the way along. And you don't have to do that, but I will, because there we go. This thing is now IMP, inosine monophosphate. Okay, there you go. So here's the overview of the whole pathway. Here, I have to lift it up a bit. There we go. Start all the way up here with ribose 5-phosphate. We add all these different atoms one at a time. Add an N, then we had 3 here, glycine, CCN, then we had CN, all the way through. It's logical if you start to think about it. Okay, we're going to add Q twice. We're going to add D once. When D adds, it comes off as fumarate. We have to add CO2 in one of the cases, formate, which is produced from methylene THF, which is produced from glycine, which is another, glycine's right up here, and it all unifies together. If you see it like a jigsaw puzzle, it's very manageable to learn this. Now, of course, we haven't made A or G yet. Okay, they're kind of like steroids. The first steroid we produced was lanosterol, which isn't really used for anything. And then from the first, in this case, IMP is used for a few things, hardly at all, but it's used in wobble in some of the tRNAs. Much more important bases are like the much more important steroids that are all produced from lanosterol. Here we're going to have to produce A and G from IMP in a much easier process. But this very first process to produce the first purine is IMP, is this thing. Okay, so this is called purine biosynthesis to IMP.